do with neural translation using multiple Apache tools. So take it away, guys.
Hi everyone, good evening, and thanks for coming to this talk. So I'm Sunil Marti and this is Jon Gottman, and we both work on OpenNLP and a bunch of other Apache projects, and we are members of Apache Foundation. So today we'll be talking about machine translation. So before we start, show of hands, how many guys actually have a use case that's involving machine translation here? And how many of you guys use neural networks or neural machine translation as opposed to statistical? Okay, great. So towards the agenda for today is we'll be talking about what is machine translation, what is neural machine translation, and what are the challenges with that, and how do you actually train your models offline in a batch mode and call them in inference pipeline in real-time streaming mode. And we'll have a small demo. I do need some help and support from you guys for the demo because the demo gods have not been good to me of late. How many of you guys here speak native German? Native German speakers? Okay, 3. Well, I was hoping that you guys could tweet in German and, with the FOSDEM hashtags, and we could actually translate those tweets in real time. But anyway, it's okay. If without the hashtag, we'll just go with German tweets. And let me just warn you that most German tweets, they die after 4 p.m. Berlin time. That's when they go to beer bars. Or before that, it's either racist or profane or, one of those different categories of tweets. With that, let me hand over to Johan. He'll take us to the next few slides.
So for this talk, we're using Apache Flink. That's a distributed streaming pipeline framework. And we have Apache OpenNLP. This is used for the pre-processing of the text we will feed to the machine translation system in the demo. And let me start with what is machine translation. So we have here this definition. We have E, that's the string in the target language. That's the language maybe I speak and I would like to translate to. And we have F, it's a string in the source language, maybe the one I don't speak, like Spanish, for example. And now we want to maximize the probability of E, and the best translation from the model we have is the one with the highest probability. So let's look at how we can translate one word. So for one word, you would just go to a dictionary and look it up there. Here we have the example of a Gebäude, and we could translate this to these 3 words, like building, house, or tower. Now the thing is that 2 of the words, building and house, are much more frequent than tower. But still, you would need somehow maybe you would need to look at the context to see which words you want to use. Which brings us to the parallel text. That's a sentence in some source language, and then you also have the translation of this sentence. And here we have one example again. Das Gebäude ist hoch, and the English translation is the building is high. And here you see I have 4 words in German, which more or less directly translate to English. And probably with this sentence I would get pretty far with a dictionary. And but there are more complicated cases. For example, this one, das ist ein Hochhaus. And here, Hochhaus would translate to 3 words in the target language. And my model would need to deal with this problem because also the sequence length is now not the same anymore, so I have more words in the output. Also, in other cases, I can have swaps, so maybe I have to translate one word and then it would appear maybe at the beginning of the sentence or somewhere else that wasn't the original sentence. So now we come to the neural machine translation part, and there's this very nice slide about the encoder-decoder architecture, and this is what is used most these days. This is a bit of a simplification. We will extend it in the next slides and add more. So on the left part, we have the encoder part, on the right is the decoder. And what we are doing here is we are inputting one sentence, that is, he loved to eat. And then we hope we are getting out, liebte zu essen. So here we have the embedding layer on the left part. And we would take the word he, and this would be pushed into the model. And the first thing we have to do is the word itself, we can't really use much. So we would go to a dictionary And this dictionary would give back a vector representation of this word. We have some slides about this, and Sunil will speak about it. So we have then a vector for the word he, and this gets pushed into the encoder. And this process is repeated for every word, and here this is just like written out, but it could also be more steps or less steps, depending on how many words you have. At the end of this process, that's the encoding phase, we end up with this S in the middle. And this S is a vector representation of the sentence. So basically, just imagine somebody tells you a sentence, and you have to remember this sentence. And that's kind of what's inside this S. And this meaning of the sentence, which is now captured in this vector, is then handed over to the decoding part of the system. So, and there I have now two inputs. The first is the S, and the second input is the null at the bottom. And now my decoder knows I would like to decode the first word of my translation, which in this case would be air. And now I just repeat this. I again give as input the S, and now I input as well the first word which was translated. In this case, that's the air. And this process gets repeated until the entire sequence is decoded and I have my translation. To make this work a bit better, this is usually done with something they call attention. And the attention helps me now that on the decoding part, I can look back onto the source sentence. That's like when you have some sentence written down, and you can just always go back to it and see what's written there while you're writing your translation, so you don't really have to remember everything. And with the attention, this can look on the decoding part back to the part it just wants to translate. So maybe it's looking here at the, here's like, ich bin ein Student, and the translation is I am a student. So maybe I am at the student at the end, and it knows, okay, I can look at the student word in my input sentence and see how this should be translated. But of course, this is much more complex, and these days, people would usually use something called a transform model, which has like many, many layers for the attention. And at the end, you have the softmax, which would then output the word. This is attention is all you need. So if you want to learn more about this, maybe go to this paper, have a look. This probably takes a bit of time to understand this in detail. And so the upper function, that's the softmax function, which is used to calculate the probability of the output words. And the second function, that's the entropy, and that's a loss function which is used for training. Because during training, you kind of like initialize everything randomly, and then you want to figure out parameters which can be used for the translation. So you run the computation once forward, then you get something out, and the loss function then can tell you how you should change your parameters. And this process usually repeats millions and millions of times until you have some weights which actually then give you the translation. Training can take a long time, and also depends on how much data you are training on. So why do we do NMT these days? Because it just works much better than what we had before. From around 2015, NMT started to work, and 2016 it was already better than the SMT, the statistical machine translation, which was before. And since 2017, nobody is doing any more SMT. So here I'm handing back to Sunil, and he will go through some samples.
So before we go through the samples, just a quick note on the previous slides. So what happened here, if you look at this graph, what happened between 2015 and 2016? If you see in 2016, the orange bar is way up the blue bar. So that's when Google Translate switched from their traditional statistical machine translation to neural machine translation using attention mechanism. And the advantage of using attention mechanism is that translation happens based on the context. It's not just, you're not looking at, let's say, the 3 words or 4 words before translating this particular word. You're looking at the complete context, like 3 sentences ahead and 3 sentences behind to come up with a better translation. So on that note, sometimes you do see that the machine translation goes all whack, and you may see something very frivolous, and fun stuff come out of it. Some examples here. So those of you who speak German, what do you think that is? Is it good, or is it nearly good, or is it near? Okay, so next example. Okay, so even better. If you have been using Twitter or the browser, and can anyone tell me the difference between the original and the translation here? Okay, so it's not Dutch, and when you translate from a mathematical function and you put spaces in between the plus signs, it's a Dutch. It becomes Dutch, right? That's not true. So yeah, that's Twitter, Microsoft Bing. That's what Twitter uses for translation. So how do we avoid those kind of challenges with machine translation? So the first thing to look at is what is the kind of input that you would expect for machine translation. And since we are dealing with neural machine translation, since we are dealing with neural networks here, the input to most neural networks is a vector. Vector is area of numbers. And the training data for this, since we are dealing with sequence-to-sequence models, you have two parallel training corpuses coming through, and it's parallel text. Now the challenge is how do you represent a word from the text into a vector, convert that into a feature store. So the most common way of doing that today is something called an embedding layer. You create an embedding layer as your input layer. So let's say if my input has the vocabulary dog, cat, giraffe, fox, bird, etc. And for each of them, I randomly initialize each of them. Dog is a vector of, the vector of this, the string here, the numbers here. Same with the cat. So I start off with initial random initialization, and I run it through something called a word-to-vec. I convert that into a word-to-vec. And so once I convert that into a word-to-vec, and this is what I get. It kind of learns the real values and comes up with better values than what I started off with randomly. So the one big challenge we have with building machine translation models is, especially languages like German, which have huge vocabulary and extremely long comprehensions that are impossible to pronounce. How do you deal with those unseen vocabulary? And the text you get for training is very limited. It's got very limited vocabulary. For example, the demo I'll be showing you, it's a German to English neural machine translation model. And it was trained with only 30,000 German words. But I kind of found that it can handle the rest of the unseen words. So how do you handle the unseen vocabulary? Okay, so let's say if my text has only 30,000 words, what do I do about the rest of the vocabulary? How do I account for that? So this was one of the challenges that was solved by something called byte pair encoding, BPE as they call it. And here's the paper about that from University of Edinburgh. And so the way byte pair encoding works is, if this is my input text, positional, addition, contextual, I take the most frequently occurring consecutive bytes and replace that by a different byte. So an example is, here in this, I see that TI and TI are occurring more often. So I can replace TI with an X. Now I can kind of go that path recursively. I can replace IX and IX with something else. And I can, my input size becomes from this to this. It kind of narrows down my input size. So yeah, I can keep going recursively on this. So yeah. So what you had becomes this finally. So your input size, it's kind of like a model compression. Your eventually model size is going to be much smaller than what it would have been without byte pair encoding. So, and your models can, they're storing a function, they're learning the translations, and they can decode that back. So, and the other challenge that we have is, if you're training deep learning models, you're dealing with a cluster of GPUs. And if your input text comes as, with different lengths, if the input, one of them is very small, like only 5 words, the next sentence has got 20 words. And if your input text is kind of not in a good order, it's not sorted up front, then you're not optimally utilizing your GPU cluster. So you deal with something called jagged tensors. And this is how it would look. So if the max vocabulary size is 17 per sentence, so if the first one has only 14, the next one 4, blah, blah, blah. So you can kind of see that it's not sorted out. So it makes sense to pre-sort your input upfront before sending it to the GPUs for training your models. And so this is how you would do that. And now you can break this up into chunks and send each chunk to different GPUs on the cluster for training. So those different batches. Okay, so this is how you do the model training. And so the thing that we have taken into factor here is, number one, create an embedding layer and use byte pair encoding to account for unseen words, and then sort your inputs to avoid jagged tensors and optimally utilize your GPUs. So you have trained your machine learning model, attention network model offline in a batch mode. Now, how do you deploy that in a streaming pipeline for real-time inference or real-time, if I'm Amazon and if I want to translate my content into from German to English or English to French? How do I do that in real time? So that's where you can, we'll be looking at, that's the next part of the talk, streaming pipelines. So for this particular demo, we have used Flink. Since we had a talk about Beam this morning, we can as well use Beam with a Flink binding. And the normal steps in any natural language processing is you do a language detection first, and then you do a sentence detection. So break up your input into sentences based on the language, and then you tokenize each sentence into individual words, and then you run your byte pair encoding. So the model in this case, I've deployed the model on Amazon SageMaker, but you can as well run it as an RPC server locally or use any model server. So here's the complete pipeline in Flink for this demo. And I just got the, yeah. So this is how the inference pipeline would look. So for this demo, I'll be using Twitter as input source. And I'm running it through an OpenNLP, bunch of OpenNLP for sentence detection for German. And I'm using an RPC client for doing the demo, for running the inference. So here is where I need some help from you guys. The Germans can, if they can start tweeting, I would really appreciate that. If not, I'll just pull the German tweet feed as is. Okay. Ready? Okay. Let me uncomment my German. So it's starting up a Flink cluster, and I'm running this as a Flink job. I'm putting the job on the cluster, and it's going to be making an RPC call to SageMaker. REST API call to SageMaker for getting the model inference. So let's wait for the tweets to come. FOSDEM hashtag German tweets, please. FOSDEM 2019 or FOSDEM 19, either one. I mean, if that doesn't work, that's fine. I can just pull off the normal German tweet feed. So while that's running, any questions that you would like to answer? Okay, I'm not having luck with FOSDEM hashtag in German, so let me just comment that out and just run the normal one. Okay. Yeah, that's not FOSDEM tweet, but anyway, that's a German tweet. Okay, so the first line is the actual German tweet, and the second one is a translation. The line following that is a translation in English. So I guess, what do you think about the translation? Is it good? I think it's pretty good compared to Google Translate. It's as good as Google Translate, if not better. I'm critical of Poland when you start to shut down Windows, namely. Okay, yeah. Anyway, so this is, yeah, some of them are abusive and racist, so let's ignore that. Yeah. Okay, so any questions? So here are some links. The attention paper from Google, attention is all you need. And the slides, we'll update the slides. Yeah. Questions, please. Yeah. One, yeah. Yeah, we use byte pair encoding. So byte pair encoding is, you take every successive bytes and replace that with a common byte. Yeah. So basically, what the advantage of that is your model size is much smaller, and it's kind of like a data compression. So it's a smart technique. Yeah. 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 Okay, so the one thing I did not mention is this model was trained using World Machine Translation WMT corpus, or Europal corpus, and it's all open source. But and I had used only 30,000 words, German words, in the actual training model. Okay, but nevertheless, it works fine for all kinds of tweets that come through. So if you look at this, for technical stuff, I would say. It's the same size. You can train it on Wikipedia. You should be fine too. We have trained it on Wikipedia or any technical stuff. Yeah, I mean, if you're using byte pair encoding, I think you pretty much cover most. It's more. You can generalize your model to cover technical text as well as tweets as well as news. Yeah. Time's up. Yeah. Thank you.
I can answer this, yeah? Sorry.
Repeat the question.
So how do you translate long German words, right? You don't really have in your dictionary? This is a question? Okay, yeah. So the way this, So the way this works is the BPE will compress the word to smaller units, and the model knows how to translate these little parts of the words. So it doesn't really look at the entire word, but it's like the new tokens it gets from the BPE process, and that's why this works. Any more questions? Okay. Yeah. You can take it off here and then clip if you want. I don't know. And you're speaking along, right? It's easier, I guess. So I have to put somewhere in your pocket. I would put it close up, so you speak rather loud. It's very better acoustics.
Okay. Oh, okay. Okay. See it.